we are for the second video lecture of chapter 24, what's going to be the last video lecture of the semester. We need to finish up the chapter on analysis of variance. So in the first half of this chapter, the first video lecture, I was talking about basically what the analysis of variance does. Remember that it is going to compare variation between samples, that's our mean square for groups, to variation within samples, what's called the mean square for error. When we divide the variation within samples, variation between samples by the variation within samples, we get what's called our F statistic. This is named after Ronald Fisher, who was a statistician back in the early 1900s who developed many of these statistical tests that we use. So what we're doing here then is looking at a ratio of variation between samples to variation within. And remember that if we have more variation between our samples than within our samples, that should give us a large value of F and a small p-value. That should be an indication that our samples do come from different populations. If the reverse is true, if we have more variation within our samples than between our samples, that should give us a small value of F and therefore a large p-value, and that should be an indication that our samples come from the same population. All right, so how are we calculating mean square for groups and mean square for error? Mean square for groups is a statistic called sum of square for groups divided by k minus 1. K is the number of samples that we have. So in the rat example where they were fed different diets, there were 3 different groups fed 3 different diets. That's k. It'd be 3 minus 1, so this would be 2. That's our degrees of freedom for our numerator calculation. For sum of squares for error, which is our denominator, that is our total sample size minus the number of sample means that we have. So for our rats, I think we had 50 actual data points minus 3 groups of rats, so 47. That's our degrees of freedom for our numerator. So I'm going to show you how to calculate sum of square for groups and sum of square for error here in just a moment. And you're not going to have to do those calculations yourself, but you are going to see these two statistics on the ANOVA output table, so it's important to know what they are. All right. Remember that with analysis of variance, when we ANOVA, our null hypothesis is that all of our population means are the same. This is just another way of saying that our samples all come from the same population. The alternative hypothesis is just that that's not true. All right. So our F statistic then has a distribution that looks like this. It's skewed to the right. It's always positive because we are squaring sums, right? So when you square, you always get rid of negative signs. That's why this is always positive. And so we're looking for a value of F where that falls on that x-axis and then calculating an area to the right of that. And if we set our alpha at 0.05, this is our 0.05 cutoff. That means 5% of our area to the right. If we have an F statistic that falls to the right of that, that means we have a p-value less than 0.05. Okay, so that's what how we're doing this, all right? Okay. The F distribution has numerator degrees of freedom of k minus 1, as I said here, and denominator degrees of freedom of n minus k, as we see there, all right? Okay, so how do we calculate F? Let me fill some of this in here real quick. Okay, so again, we need our mean square for groups and our mean square for error. Mean square for groups is variation between our sample means, and mean square for error is variation within our samples. Okay, so mean square for groups. This is a variance of the means that's weighted for sample size, and basically it measures the variability between our sample averages. All right, so let's say that we have 3 sample averages, 3 sample means. We could add up those 3 means and divide by 3. That would give us a mean of those 3 means, what's called a grand mean or an overall mean. That's what you see right here. So this second term in each of these parentheses is the grand mean, or the overall mean. It's the mean of this sample mean and that one and that one. If we add up these sample means and divide by the number of means we have, we get the grand mean, or the overall mean. So for sample 1, we take that sample mean and subtract the overall mean from it, square that difference, and multiply it by the size of sample 1. We then do the same thing for sample 2. Average of, or the sample mean for sample 2 minus the overall mean of all the samples, square that difference, and multiply that by the size of sample 2, and so on for all the rest of our samples. We then add all of those up. That's why this is called sum of squares, sum of square differences. We divide that sum, the numerator, by k minus 1, number of samples minus 1. So if we had 3 samples, this would be 2. We divide by 2. That gives us our mean square for groups, okay? All right, mean square for error, the denominator in our calculation for f. This is the mean square for error. Sometimes you see it referred to as the pooled sample variance, or SP squared. It's the average sample variance that's weighted for sample size. Again, it measures the variability within each of our samples. All right, so how do we do that? So mean square for error. We have to take the variance, that's S squared, the variance for each of our samples, and multiply that by the degrees of freedom for that sample, n minus 1. So variance of sample 1 multiplied by the size of sample 1 minus 1. Do the same thing for sample 2 and sample 3 and so on. We then add them all up. So that is going to be then divided by n minus k, the total number of measurements we have across all of our samples minus the number of sample means that we have. So if we have 50 measurements across 3 samples, 50 minus 3, 47. That gives us our mean square for error, which is our denominator in our calculation for f. All right, again, you're not going to have to do this calculation or this calculation, but you are going to see these numbers in the ANOVA table, and you need to therefore know where they come from. All right? Okay, so now once we've calculated our F statistic, we're going to use table F to find that F statistic. So the F distribution is an asymmetrical distribution. It has 2 distinct degrees of freedom, numerator and denominator. All right, and again, Ronald Fisher was the one who developed this back in early 1900s sometime. So again, we're going to calculate, as with other tests we've done, we're going to calculate a statistic, in this case the F statistic, from our sample data, look it up on table F in this case, and that will help us find the area to the right, which is going to be our p-value. All right, so let's look at this table, and I gave you this table in your handouts at the beginning of the semester, so you should have a copy of this. Okay, so with table F, we have 2 degrees of freedom. Across the top, we have our degrees of freedom for our numerator. On the side, we have the degrees of freedom for our denominator. So again, numerator degrees of freedom is number of samples minus 1. Denominator degrees of freedom is the total sample size across all of our samples minus the number of samples that we have, so n minus k. All right, so let's say that we have degrees of freedom of 5 in the numerator and 4 in the denominator. That means we are looking at numerator degrees of freedom of 5, we're looking in this column, and denominator degrees of freedom of 4, we're looking in this row. So we're looking right there. Now, where does our F statistic fall in that? Let's say our F statistic is, let's say it's 14, right? So 14 lies between 9.36 and 15.52. So you come over here and you see, okay, well, all you can say is that your p-value is between 0.01 and 0.025. So it gives you a range for your p-value, right? So you're just finding your F statistic in this range of numbers and figuring out what p-value it relates to, or what range of p-values it falls between, okay? All right, so as a reminder, our F statistic equals the mean square for groups over the mean square for error. This is a measure of variation between our sample means This is the measure of variation within our sample means. All right, so remember, mean square for groups is sum of square for groups over k minus 1. Mean square for error is sum of squares for error over n minus k. And these values are given in the ANOVA table, so that's why I'm pointing this out. All right. So let's look at the ANOVA table for the rat diet example we've been looking at. Okay, so remember we have 3 samples. We have one here for the rats on chow, one for the rats on restricted diet, one for those on extended diet. All right, this is our ANOVA table. The main thing we're looking at here is p-value. You see it's 0. So that's telling you that somewhere between these 3 means, there's at least one significant difference. It could be between chow and restricted, or chow and extended, or it could be between restricted and extended. We don't know of those 3 possibilities where it lies. It could be more than one of them. All this p-value tells us is that somewhere in here, there's at least one significant difference between 2 means. Okay, now, what do we have in our table? Well, first of all, this first row called the factor, that is your mean square for groups row. Remember that. That is groups. The second row called error, that's your mean square for error. So 31,700, that's your mean square for groups. That's your numerator in the calculation of F. 2961, that's mean square for error. That's the denominator in the calculation for F. If you divide 31,700 by 2961, you get F, which is 10.71. Look that up on a table with the given numerator and denominator degrees of freedom, get a p-value of 0. All right, so follow this arrow down, right? Look at the color coding. Blue, 31,700, that's your mean square for groups. That is found by taking sum of square for groups and dividing by k minus 1. This is your sum of square for groups. This is degrees of freedom k minus 1. 63,400 divided by 2 gives you 31,700. That's what this is saying. All right. Mean square for error, 2961. Go down here, notice the green. Mean square for error is sum of squares for error divided by n minus k. So sum of squares for error divided by n minus k. 50 minus 3 is 47. Divide this by this, and you get 2961. So now we have our mean square for groups, mean square for error, calculated from our sum of squares for groups and error, and our respective numerator and denominator degrees of freedom. That leads us to calculate F. I'm pointing these out here because you may well have an incomplete ANOVA table on your exam, and you will need to fill it in. That means you have to understand the relationship between these numbers. And that's why I have broken this down as I have with the color coding, so that you know where all those numbers in the table come from. This final row for total, you can pretty much disregard. We don't really use that, okay? You're only concerned about the factor and the error rows, or the groups in the error row. All right, so let's move on. So in our example here, we had a degrees of freedom of, for our groups, of 2. And for that, you see that we have a highly skewed F distribution. So if you look up our F value of 10.71, you see it is like way over here. And the area to the right of that is extremely small. And that's where that p-value of 0 came from. So based on that very, very small p-value, we're going to reject our null hypothesis. In other words, the alternative is probably true. And the alternative would say that the population mean weights are not all the same. In other words, what diet these rats were fed has a significant effect on their weight gain in male rats, all right? Now, when you look at table F, okay, for a degrees of freedom in the denominator of 47, there is no 47 row. There's a 25 and a 50. So all you can do then is go to the next lower degrees of freedom, which is 25, and find the last number in that. So numerator degrees of freedom of 2, we see that we have the final value of 9.22 as an F. Well, ours is 10.71. So as we come down, as our F values get larger, note our p values get smaller. So our F lies under 9.22, so all we can say from the table is that it's less than 0.001. Minitab tells you precisely that it's very small, right? 10 to the minus fourth. So effectively 0. Okay, so let's compare an ANOVA to a t-test. So remember I said that the reason for using an ANOVA is that you're comparing more than 2 sample means to each other, 3 or more. You can't do that with a t-test. With a t-test, the most you can compare together is 2, so a 2-sample t-test. Now let's say that you had 2 samples. Could you run a t-test or an ANOVA on that? Sure, you could. The ANOVA and a 2-sample t-test when you're comparing just 2 samples are functionally equivalent. They are the same as each other. Okay, notice that your hypotheses are the same in both cases. In one, you're calculating an F statistic, the other a T statistic, but F is just T squared. And you would get precisely the same p-values in both of those. So why would you do a t-test when you could do the ANOVA? Well, a t-test gives you more flexibility. Okay, it gives you a one-sided alternative that you don't have with the ANOVA. The ANOVA is always two-sided, right? That is a two-sided alternative. With the 2-sample t-test, you could do the one-sided alternative if it was more appropriate for the situation you were dealing with. All right. Also, if you're not sure that the 2 populations have the same standard deviation, you might want to run the t-test and select assume unequal variances. That sort of protects you against that unequal variance problem. With the ANOVA, all you can do is look to see if your standard deviations are equivalent. There's that rule about the largest standard deviation not being more than twice the smallest. So if you're not sure about that, if you think you might be violating that, you could do a 2-sample t-test and check assume unequal variance, and that helps to protect you a little bit, okay? But basically, if you have 3 or more samples, you have to do the ANOVA. If you have 2 samples, just do a t-test. It's cleaner. You have more options. All right. So what about interpreting our results from the ANOVA? Well, again, with the ANOVA, our null hypothesis says that all population means are equal, while the alternative just says that that's not true. So a significant p-value then leads us to reject our null, indicating that not all of our means are equal. But you don't know which of the means are unequal from each other. You don't know which comparisons this is referring to. So we have to do either summary graphs, like a box plot or an interval plot, which is what we're going to do next, or you can actually do follow-up statistical tests of significance, and that's covered in chapter 26, but those are frankly beyond the scope of this class, and we don't have time for it anyway. So we're going to use some summary plots to sort of figure out where that significant difference might lie. Okay, so let's look at our RAD example again. So remember that we have our averages plotted here with our red dot. You can see that they sort of arc up. It looks like, restricted and extended are having an effect, but we don't know if this is significantly different. The ANOVA test with the p-value tells us it is, but we don't know if the difference lies between these two means, or between these 2 means. Okay, so our summary plots are going to help us to figure this out, all right? Okay, to do that, though, we need to calculate a 95% confidence interval. That's going to allow us to then compare these means to each other, right? So basically what it's going to do is create a confidence interval around each of the means, and the way this is going to work is that if the confidence intervals overlap, as you see here, lots of overlap, that would be an indication that that p-value is greater than our alpha. However, if there's no overlap, as you see there, that would be an indication that our p-value is less than our alpha. So we can use this interval plot here to figure out where the difference lies, but we have to be able to calculate that 95% confidence interval, and that's what we're going to talk about next. All right, so we have, again, our mean square error, right? That is also often referred to, as I said, as the pooled sample variance, or SP squared, okay? It estimates, again, the common variance between, within our populations, within our samples, all right? This is our denominator in the calculation of f. So we're going to calculate a confidence interval for each of our sample means. And so in effect, we're calculating confidence intervals for each of our population means. And the way that we do that is shown below, all right? So now there's two different calculations here, or formulas. They're both the same thing. I actually prefer to use this one because it's using something, mean square error, that we've been talking about. Here you have the pooled variance, which we haven't talked a lot about. But basically what we're going to do is find a value of t, because remember I said ANOVA and t-test are functionally equivalent, so we're going to use a critical value of t, multiply that by our pooled variance divided by the square root of n. Or, again, that value of t multiplied by the mean square error divided by the sample size and taking the square root of, okay? Either way, this gives us a margin of error. Remember, margin of error is 1/2 of our 95% confidence interval, or of our confidence interval. So our mean minus and our mean plus, the margin of error, gives us our confidence interval. Okay, now, how do we find our critical value of t? Well, we're going to use our t-table, which is table C, and we're going to look at n minus k degrees of freedom for the appropriate row. All right, so let's go back and look at the RAD example. So here we have our ANOVA table that I showed you before. Remember, small p-value, but we need to figure out what's driving that significance, okay? Now, in Minitab, you can tell, in terms of the test options, you can tell it to print interval plot, a rudimentary one, for you. So what we've got here is a mean of 605.63 for the Chow group. That's right there. And you see the 95% confidence interval around it. Here's the mean for the extended group and its interval, and the mean for the restricted group and its interval, the mean for the extended and its interval. So notice we have overlap between extended and restricted confidence intervals. There is no overlap between Chow and restricted. It's close, they seem to butt up to each other, but they don't overlap. So that right there is driving some of our significance. If you did a t-test on these two means, you might see a p-value of 0.05 or just a little bit less than that. Now compare this confidence interval for Chow to this one for extended. There is no overlap between this one and this one. That's what's driving our significance. If you do a t-test on that, you'll get a p-value much less than 0.05. Okay, so our confidence interval then is our sample mean, so sample mean 1, for example, down here, plus or minus our critical value of t times our pooled sample variance divided by the square root of n. All right, so on table C, if you look at degrees of freedom of 47, because that is your denominator degrees of freedom, and 95% at the top, follow that column down to the row of for 47, or one equivalent to it, what you get is a test statistic of 2.012. That's a critical value of t. So sample mean of 605.63 plus or minus 2.012 times our pooled sample, our standard deviation, right there, divided by the square root of our sample size for sample 1, 19, and you get this margin of error. So our confidence interval right here is 605.63 as our mean, plus 25.12, plus, and then minus 25.12. So that defines our limits of our interval with our sample mean right in between. And we also did that same for this sample mean and for that one to get their intervals. Okay. Now we can compare those intervals directly. All right, let's look at another example. We have 3 varieties of tropical plant heliconia are being studied. And here are the flower lengths in millimeters for 3 independent random samples. So first sample here, second sample there, third sample there. So Baha'i, red, and yellow are different varieties of this plant. And they want to know, do these plants have significantly different flower lengths? So our null hypothesis then is going to be simply that all population mean flower lengths are the same. The alternative is simply that that's not true. All right, are the ANOVA assumptions satisfied? Well, it tells you that we have 3 independent random samples, so the random sample requirement is satisfied. We look at for skew. There's no skew there, that looks pretty normal. this one might be a little bit skewed. That one certainly is skewed. But overall, we have, I think, about sample size of 53 or 54, so we're above 40, so we can ignore that skew. So we're good there. We need to look at summary statistics for the equal standard deviations requirement, and we'll get to that here in a minute. All right, now as far as the interpretation, they've done this as a box plot, and I absolutely hate box plots. You can't look at this and see, just by looking at it, if there are any significant differences. Remember, for a box plot, you have the minimum value and the maximum value as the ends of your whiskers. Then you have Q1, Q3, with your median, and now they plot the average or the mean in that. There are 6 different statistics in there. And the difference between the top of the whisker and the bottom is not a confidence interval, so you can't compare overlap to figure out what's significantly different. As far as I'm concerned, these plots are basically useless for inference. All right, so what do we use instead? An interval plot. These are much better, right? Dr. McCandless loves interval plots, remember that. So here now you see we have our 3 means for our 3 varieties plotted and their respective 95% confidence intervals. There's no overlap between any of them. And look at this huge difference between the bottom of this confidence interval for Baha'i and the top of this one for yellow. That is what's driving most of your significance. This is driving some of it as well, and then this is driving some of it. They're all 3 significantly different from each other, but you can't tell any of that from these box plots. Useless, right? This is what you want, an interval plot. Okay, so let's take a look at the actual ANOVA output here. All right, so here's our ANOVA F table, okay? We have a p-value of 0. Why? Look at that huge value of F. That's enormous. If you go down here, you see your p-value is 10 to the negative 27th. That is a decimal, 26 zeros, and a 1. That's a 0 p-value, and it's because of that huge value of F, okay? And here again, you see the interval plot, which is showing you that there's no overlap between those, so they are significantly different. Now, what about our assumption of equal standard deviations? Let's look at that. Remember, the rule here is that your largest standard deviation can be no more than twice your smallest. Well, 0.975 is our smallest, 1.799 is our largest. If you double 0.975, you get about, what, 1.95? So this is smaller than that. This number is not twice this number, so we're good. We can do the ANOVA on this, and we already talked about the other assumptions in the previous slide or two, okay? So we know from our p-value right here that there's at least one of these that's different from the others. We know from looking at it further with an interval plot that they're all significantly different from each other, and the relatively huge differences between them is why we have this small p-value and that large F statistic. Okay, so we've not done a t-test because a t-test, doing multiple comparisons here between 3 or more samples, would increase our risk of making a type 1 error. It would compound that 0.05% chance of making that type 1 error at alpha 0.05. Instead, we use an ANOVA to get around that problem, and we've been able to find that there is an overall level of significance through our p-value, and through an interval plot, we've identified where those significant differences lie. All right, that is it for ANOVA, and that is the